This is the second video for the lesson, More Than Meets the Eye, Transformations of Quadratic Functions. In this lesson video, we will focus on vertical and horizontal dilations and applying multiple transformations. So let's dig in. In transformation form, we have been studying translations, reflections, and now dilations. So we'll be focusing on the a value as it's happening outside the function. So it's a times the function, and so that'll be our vertical transformation or vertical dilation. And we're also going to be focusing on the b value, which is happening inside the function. So that will be our horizontal dilation. So let's first look at vertical dilations. So for instance, if I start with my basic function of x squared, and now I want to multiply that function by a factor of 2, we're actually going to be dilating by a factor of 2. So we're going to see what happens, but then what happens if I multiply the function by 1/2? So graphically, you can investigate that. So the first, when I multiply the function by 2, notice that it is becoming narrower. And when I multiply by a factor of 1/2, it's becoming wider. So one of the reasons why this is happening is that when I'm stretching, if you can see here in the red, when your a value is greater than 1, so our a value was 2, then it's stretched vertically. So my graph is being stretched up and down, so vertically it's becoming narrower. So you can think of that stretching away from the x-axis. But when I multiply by 1/2, and it says here in red that that's when 0 or a is between 0 and 1, that it's being compressed vertically. So when I compress up and down, that's actually making it wider. So in the table of values, what does that look like, or what does that mean? Is we'll look at our table of values. The x's are staying the same, but look what's happening to my y values. My y values, remember this was 2 times g of x, my y values were being multiplied by 2. And remember, w of x was 1/2 times g of x. Look what's happening in my y values. They are being multiplied by 1/2. So that means that my y values are now, in the first one multiplied by 2, are growing at a faster rate. So therefore, it is shooting up faster. So instead of here, it's now shooting up faster. So now it's why it become narrower, versus when I start here, I'm multiplying by 1/2, so they're actually increasing at a slower rate, so I'm widening out my graph. So you could see there my coordinate rules from the table of values, and how I generalize that is whatever my a value is, I'm multiplying that by y, by my y values. So horizontally, what's happening when I multiply by 2 and 1/2 as well. But now this time, it's happening inside the argument. And I'm actually going to change that. I don't like using the same letters for the functions again. I'm going to call this P and Q. Okay, so now let's see what happens graphically. When I multiply the argument, or the x inside, by 2, what's happening? Oh, it looks just like when I did that up above by 2. So it looks like it's becoming narrower. And then when I multiply g of 1/2 x, then I can see I'm widening out. But this might be a little different than what you were expecting. Well, let's take a look here. Table of values will tell the full story. Was when I look at the x values keeping the same, something funky is happening with my y values. But if I kind of zoom in, I'm going to look at this as more as a mapping from one point to the next. So negative 416 has now become negative 216. And negative 39 has now become negative 1/2, 9. And negative 2,4 has now become negative 1,4. So remember, this was g of 2x. So that means in this case, my b value was 2. And if you notice that my x values in this case were actually being multiplied by 1/2 when my y values stayed the same. So what it's really saying, if b was 2, is that 1/b is what I am multiplying my x values by. Okay, and that's actually what happens here, is I am multiplying by 1/b, whatever my b value is. I'm multiplying that by my x values. Okay, all right, and then down below I can see that happening when I had g of 1/2 x. Again, I'm going to look at this as a mapping. Negative 416 became negative 816, and negative 39 became negative 6, 9, and you can keep following the pattern. Again, this time my b value is 1/2, but notice that my x values are now being multiplied by 2. So I'm doing 2x, y. And so that really is the inverse of 1/2 is 2 over 1, or 2x. So this still holds true to that general coordinate rule I came up with, is that how I figure that out is whatever my b value is, I do 1 over that value times my x values to get that transformation. And so just pay attention here in the red box that when you're horizontally compressing by a factor of 1 over b, so when your b is larger, so like 2, so 2 is greater than 1, you're actually multiplying 1 over b, and I am horizontally compressing, which means that I'm compressing this way and actually makes my graph narrower. If I have a value 1 over b where b is between 0 and 1, so like 1/2, I'm doing 1 over 1/2, which is by 2, and I'm actually horizontally stretching, which was widening my graph out. Okay, so to show you what we were just talking about is we were doing these dilations when the basic function was x squared. But if the basic function is not x squared, what does that look like? So let's say I start with this quadratic function, and when I multiply 2 times g of x, notice that my graph is vertically stretching away from the x-axis. And when I multiply by 1/2, that should be a vertical compression. So I am compressing the graph towards the x-axis. And we now have p of x, and that's g of 2 of x. And you can see here that I'm actually compressing horizontally towards the y-axis, or I am stretching horizontally away from the y-axis. So let's put this all together. Is what if I needed to graph without technology, and I can use my coordinate rules that I have just learned and put all together here. So this tells me if I'm given transformation form, I can write these rules and create a table of values, and then I can graph my new transform function. So it is giving me that if the basic function x squared, we want to transform it in this way. So let's kind of break down what's happening. The 2 is my a value. If you remember, that is a vertical stretch or dilation by a factor of 2. I have no b value, but my c value here, when it's +3, that actually means my c value is -3. So that is a horizontal, I'm going to abbreviate here, horizontal translation, and that is going left 3. And this d value is a +4, and that is a vertical translation, and that is going up 4. So I'm going to write my coordinate rule to help me find my table of values. So I know that xy is going to be mapped to, and so it's 1 over b. We don't have a b value, so it'll just be x. And it says plus c, so I'm adding -3, which is the same as subtracting 3. Then I take a times y, which is 2 times my y values, plus my d value, which is 4. And this will help me produce my new xy coordinates for my transform function. So notice I start with -3, 9. So if I start with -3, 9, I know that I'm going to take -3 minus 3, and then 2 times my y value of 9, and I'm going to add 4 to it. So this becomes -6, 22. So you could keep doing that with your values using my coordinate rule that I wrote there. 2 times the y value, add the 4, becomes -5, 12. And I'm going to go ahead and write this in because I've done the math for myself already. Let's see, -2, 6, -1, 12, and 0, 22. And then I can come over to my graph and start graphing those values. So -3, 4, -1, 6, I'm sorry, -2, 6, -1, 12, -5, 12. Well, and you're going to pretend like I can draw a really good parabola on this iPad. And you can see there I've done the transform function. And to verify with technology, my basic function, here's my transformation form, and you can see, yep, just alike. Just a perfect parabola like I drew here. And that is how you write, or you can create a table of values and a graph using transformation form without technology.